Imagine leaving Earth and reaching Mars in just 45 days. Not months, days. This isn't science fiction. It's the promise of nuclear electric propulsion, or NEP. A quiet revolution in space technology that could reshape everything we know about traveling in space. Let's talk about what makes NEP so powerful, and why scientists now believe it's our best hope for safe, efficient, and scalable missions to Mars and beyond. First, the basics. Nuclear electric propulsion works by using a nuclear reactor to generate electricity. That electricity then powers an electric thruster, usually a high-efficiency ion engine or plasma engine. This differs from traditional chemical rockets that burn fuel quickly for a massive burst of speed. NEP trades explosive power for endurance, and that's what makes it special. Because NEP engines operate continuously and efficiently over long periods, they can slowly build speed and reach incredible velocities. A traditional rocket gets you off the ground, but a NEP system keeps pushing, mile after mile, day after day. That continuous thrust means shorter trip times, less fuel, and fewer launch complications. Now let's put that into context with something you've heard about: Mars. Current space missions to Mars take 6 to 9 months. That's a long time for astronauts to be exposed to radiation, microgravity, isolation, and the risks of mechanical failure. NEP systems could cut that time by more than half, down to 45 to 60 days. That's game-changing. One of the leaders in this field is the Ad Astra rocket company. They're developing the VASIMR engine, a variable specific impulse magnetoplasma rocket. Sounds fancy, but here's the idea. It uses radio waves to ionize and heat a gas, turning it into plasma, which is then ejected at incredibly high speeds using magnetic fields. VASIMR engines can run for hours or days at a time without needing constant refueling. Then there's the SPAR initiative, run by Space Nukes and the University of Michigan. They're pushing forward with next-gen reactor designs specifically intended for electric propulsion. These aren't paper projects. They're being built, tested, and evaluated right now with support from NASA. What makes NEP systems stand apart isn't just their speed, it's their flexibility. They can power a wide range of missions: cargo holds to the moon, asteroid mining ships, crewed Mars expeditions, and even planetary defense platforms, all without relying on solar power, which weakens the farther you go from the sun. There are hurdles, of course. Launching a nuclear reactor into space is a politically sensitive topic, and managing heat from a compact space reactor is an engineering challenge. But none of these problems are unsolvable. In fact, many of them were addressed decades ago during early US and Soviet space reactor experiments. Today's NEP programs are cleaner, more efficient, and built for the long haul. Once they reach operational status, the entire architecture of space travel will shift, from explosive launch-based strategies to slow-burn, fast-arrival transport. And it doesn't stop at Mars. These same systems could one day push robotic probes to Jupiter, Saturn, even out of our solar system, with travel times cut dramatically. That's why NEP isn't just exciting, it's essential. So the next time you hear someone say we can't get to Mars, remember, the engine that could take us there is already in the lab, already being tested, and very likely to be lighting up the void of space in just a few short years. This is nuclear electric propulsion, the future of space travel, and humanity's best shot at becoming a truly interplanetary species.